The universe is not deterministic. This is not a philosophical opinion. It is a measured result of modern physics. For centuries, science assumed that perfect knowledge of the present would make the future inevitable. Classical physics treated reality as a system that could, in principle, be computed in advance. But in the 20th century, that assumption collapsed under experimental pressure, not gradually, but structurally. Quantum mechanics revealed a hard constraint at the most fundamental level. Nature does not select outcomes until interaction forces a resolution. Probabilities exist, results do not until measurement occurs. This video is a system audit of that failure. If the universe cannot be computed in advance, what exactly is the future and what responsibility does that place on us? Before we can audit the failure of determinism, we must reconstruct the model that once made it seem unavoidable. For over 2 centuries, the operating system of the universe was defined by Newtonian mechanics, which posited a direct, unbreakable link between the past and the future. This worldview was formalized in 1814 by the French mathematician Pierre-Simon Laplace. In his philosophical essay on probabilities, Laplace proposed a hypothetical intellect, now famous as Laplace's demon, that served as the ultimate state estimator. He argued that if an intelligence could know the precise position and momentum of every particle in the universe at a single instant, and if it understood all the forces acting upon them, the future would be as transparent as the past. In this model, the universe is a ballistics problem writ large. The Big Bang provided the initial velocity and angle. Everything that followed the formation of stars, the cooling of Earth, even human decisions, were merely the inevitable solution to that initial equation. Chance did not exist. What we called luck, or free will, was simply a variable we lacked the processing power to track. Under this paradigm, we were not pilots of our destiny. We were sophisticated automata executing a script written 13.8 billion years ago. If prediction is perfect in principle, why did classical physics hit a hard failure in practice? By the end of the 19th century, the deterministic model appeared invincible. Lord Kelvin, one of the giants of thermodynamics, famously declared that there was nothing new to be discovered in physics, only more precise measurements of the 6th decimal place. The system seemed complete, the ledger was balanced, but beneath the surface of this clockwork perfection, the data had begun to diverge from the model. The audit of classical determinism does not begin with a philosophical debate about human agency. It begins with a discrepancy in the laboratory. The failure point occurred around 1900. It did not come from the vast complexities of the cosmos, but from the simple behavior of heat and light. When physicists attempted to apply Newton's rigid laws to the microscopic world of atoms and radiation, the equations didn't just become inaccurate, they broke down completely. The comfortable assumption that randomness was merely ignorance in disguise was about to be dismantled by a new violent reality. The file opens in 1900. The anomaly is not philosophical, it's numerical. The first major crack in the deterministic edifice appeared when physicists asked a seemingly trivial question: how does a hot object release energy? In the late 19th century, this was known as the black-body radiation problem. Imagine a perfectly insulated oven with a small hole. As you heat the oven, the walls radiate electromagnetic waves that bounce around inside until they reach equilibrium. According to the classical laws of thermodynamics and electromagnetism, the same laws that govern planetary orbits and steam engines, the energy radiated should depend on the wavelength of the light. The prevailing model, formalized as the Rayleigh-Jeans law, treated energy as a continuous fluid-like variable. It predicted that as the wavelength of radiation got shorter, the intensity of that radiation would increase without limit. For long waves like infrared or red light, the math worked. But as the calculations moved toward the ultraviolet end of the spectrum, the equation malfunctioned. It predicted that the energy output would spike upward toward infinity. This was not merely a calculation error, it was a blue screen of death. For classical physics assigned that the underlying assumptions had failed not just the math. If the deterministic model were correct, even ordinary thermal objects would emit unbounded amounts of high-frequency radiation, rendering stable matter and life impossible. Clearly, the universe was not incinerating itself every time a fire was lit. The classical prediction was a catastrophic divergence from reality. The math said infinity. The thermometer said safe. This discrepancy, famously termed the ultraviolet catastrophe, was the first undeniable evidence that the smooth, continuous laws of Newton and Maxwell could not describe the fundamental granularity of the world. The system had crashed and a patch was urgently required. A theory that predicts infinity is not slightly wrong, it is structurally broken. What had to change? In 1900, a German physicist named Max Planck stepped forward to fix the code. Planck was a conservative scientist. He had no desire to overthrow the established order of physics. He simply wanted the math to match the experimental data. To force the equation to align with reality, Planck introduced a radical, desperate postulate. He suggested that energy is not continuous like water flowing from a tap, but discrete, emitted in countable, indivisible units. He proposed that energy could only be emitted or absorbed in specific indivisible packets, which he called quanta. He expressed this in a deceptively simple equation, E equals h times F, where energy equals the frequency of radiation, multiplied by a new fundamental number known as Planck's constant. This constant sets a minimum scale for energy exchange, a limit on how finely physical processes can be divided. By chopping energy into these finite packets, Planck prevented the mathematical explosion at high frequencies. In the ultraviolet range, the energy required to create a single quantum is so high that the probability of it happening drops to near zero. The curve of the graph bends back down, the infinite energy vanishes, and the oven becomes safe again. Planck viewed this merely as a mathematical trick, a formal assumption to make the ledger balance. He did not realize he had rewritten the ontology of the universe. By quantizing energy, he destroyed the ancient idea of natura non facit saltus, meaning that nature does not make jumps, a principle implicitly required by continuous and deterministic laws. The smooth continuity required for a deterministic clockwork universe was gone. In its place was a reality made of jagged, discrete steps. If energy comes in discrete packets, is certainty also discretized, or does determinism survive elsewhere? When the quantum anomaly surfaced, the initial reaction from much of the scientific community was skepticism. Surely this randomness was just a lack of data. After all, we encounter unpredictability every day, and it never threatens the laws of physics. Take the humble coin toss. It is a familiar symbol of chance. In the macroscopic world, when you flip a coin, the result appears random. But this is an illusion of complexity, not a fundamental feature of reality. In a study led by mathematician Percy Diaconis at Stanford, researchers demonstrated that if you know the exact force, angular velocity, and air resistance acting on the coin, the outcome is entirely deterministic. They even built a mechanical flipper that, under controlled conditions, could make a coin land on heads with near-perfect reliability. Even in a human hand, the randomness is flawed. The study found a roughly 51% bias toward the face that was up when the coin was flipped. This is what we call deterministic chaos, or pseudo-randomness. The outcome is theoretically calculable. We simply lack the computational power or the sensory precision to track the variables in real time. The mystery is strictly epistemic. It exists only in our minds, not in the coin itself. For decades, many physicists assumed the quantum world worked the same way. They believed that an electron or a photon behaved like a very small coin, deterministic, but practically unpredictable. If we couldn't predict its behavior, it wasn't because nature was undecided. It was because we weren't looking closely enough. Unpredictable is not random. So where does true randomness enter the system? This brings us to the most famous defense of determinism in history, mounted by Albert Einstein. Einstein accepted the mathematical success of quantum mechanics, but he rejected its philosophical implications. He could not accept a universe where events occurred without a specific cause. His objection is immortalized in the phrase, "God does not play dice." Einstein proposed that quantum mechanics was an incomplete theory. He argued that just as a coin has hidden variables like its spin rate and the surrounding air pressure, quantum particles must have local hidden variables, secret internal states or instruction sets that determine their behavior before measurement. In his view, the particle knows exactly what it is doing. We simply have not discovered the mechanism yet. However, nature offered a counterexample that defied this logic: radioactive decay. Consider an atom of uranium-238. We know with high precision that its half-life is approximately 4.47 billion years. In a large sample, 50% of the atoms will decay within that time frame. But if you isolate a single atom, the predictive model collapses. Will it decay in the next second or in a billion years? There is no wear and tear on the nucleus. An atom that is a billion years old is identical to one created yesterday. There is no internal clock ticking down. When the decay event happens, it happens without a classically specifiable trigger. In the standard quantum model, the atom does not decide to decay based on hidden internal gears. The event is intrinsic, stochastic, and irreducible within the theory itself. Einstein demanded a mechanism. John Bell built the test. The audit now moves from debate to measurement. For decades, the debate between Bohr, who emphasized probabilities, and Einstein, who argued for hidden variables, remained a philosophical stalemate. It was a war of words, untestable and abstract. That changed in 1964 when a Northern Irish physicist named John Stuart Bell transformed this metaphysical argument into a rigorous mathematical constraint. Bell's genius was to construct a lie detector for the universe, a test that distinguishes between local hidden variable models and quantum predictions. He focused on the phenomenon of entanglement, where two particles are generated together and share a single quantum state. According to Einstein's local realism, these particles must carry a pre-written instruction set known as hidden variables that tells them how to behave when they are measured. It's like sending a pair of gloves to opposite ends of the galaxy. If you open one box and find a left glove, you instantly know the other is a right glove. No magic is required. The state was determined at the moment of packaging. Bell calculated the statistical correlation limits for any system that operates under this glove logic, a world where objects are real independent of observation, known as realism, and where no causal influence can propagate faster than light, known as locality. He derived an inequality, now known as Bell's inequality. It sets a hard numerical ceiling on how strongly the measurements of two separated particles can correlate if local realism is true. Think of this inequality as a speed limit for logic. In a classical universe, the correlation value S between the particles must satisfy the condition that the absolute value of S is less than or equal to 2. The number 2 is the upper bound imposed by local hidden variable theories. It is the maximum amount of agreement allowed between two independent objects with preset instruction sets. If the universe has hidden variables, the data must stay below this line. If the data crosses it, then the assumptions of classical reality are false. Bell handed physicists a binary choice: run the experiment, check the number, and find out if reality is locally real or something far stranger. This is a speed limit for local realism. If nature exceeds it, something we assumed is false. The technology to run Bell's test did not exist in the 1960s. It wasn't until 1982 at the University of Paris-Sud that a team led by Alain Aspect finally subjected the universe to this audit. Aspect's setup was elegant and precise. He generated pairs of entangled photons and sent them to detectors on opposite sides of the lab. Crucially, the detectors were equipped with polarizing filters that could change their angles at the last nanosecond while the photons were in flight. This prevented the particles from communicating or agreeing on a strategy beforehand, closing a critical loophole. The audit was a stress test of reality. Aspect measured the correlations between thousands of photon pairs and calculated the S value. If Einstein was right, the number would hit a ceiling at 2. The quantum equations, however, predicted a violation up to 2 times the square root of 2, approximately 2.828. When the data came in, the result was unambiguous. The measured value was not 2, it was approximately 2.70. The number shattered the ceiling. In subsequent, more refined experiments conducted in 2015, known as the loophole-free tests, the violation was confirmed with a statistical significance of over 40 standard deviations. To put that in perspective, in particle physics, a 5 sigma result is considered a discovery. A 40 sigma result is certainty. The classical speed limit had not just been broken, it had been obliterated. The glove analogy was dead. The particles did not have pre-written instructions. The correlation between them was stronger than any independent objects could possibly possess. The universe had failed the test of local realism. The number crosses 2, not by a little by structure. So what exactly died locality realism, or both? The violation of Bell's inequality is the irreducible result of our inquiry. It forces us to discard the comfortable notion of hidden variables. This leads to an ontological consequence that is difficult to digest. The randomness of the quantum world is not due to a lack of information. It is intrinsic. When a radioactive atom decays or a photon chooses a path, it is not following a complex internal script that we are too blind to read. It is literally improvising reality on the spot. Furthermore, the violation confirms non-locality. The two entangled photons and aspects experiment, though separated by meters or even light years, act as a single indivisible system. Measuring one does not send a signal to the other. It updates the joint quantum state of the entire system in a way that cannot be described by local causal mechanisms. The concept of here and there is blurred. Space is not the rigid separator we thought it was. We are left with a universe that is fundamentally probabilistic and deeply interconnected in ways that defy classical logic. The clockwork god of Laplace is dead replaced by a reality that is fluid open and structurally indeterminate until the moment of interaction. But this raises a terrifying question for the macroscopic observer. If the fundamental building blocks of reality exist in superposed quantum states, jumping randomly and ignoring space, why is the world we see so solid? Why doesn't this text dissolve before your eyes? If outcomes aren't pre-written, why does your chair stay put? The audit has established a disturbing baseline, the fundamental components of reality. Electrons, photons, quarks are probabilistic entities that violate local realism. They do not possess definite classical properties until interaction with another physical system. Yet as we pull back to the macroscopic scale, the world appears reassuringly solid. The chair you are sitting on does not exist in a superposition of here and there. It does not vanish when you close your eyes. The moon follows a predictable orbit indifferent to whether we observe it. This creates a paradox known as the measurement problem. If the universe is built from jittery, indeterminate bricks, how does it form such a rigid wall? For decades, this was the central mystery of quantum mechanics. The prevailing Copenhagen interpretation essentially shrugged, treating the observer as a magical off switch that collapsed the wave function. But a system audit cannot accept magic as an explanation. There must be a physical mechanism that enforces classical behavior on quantum objects. A major part of that mechanism has been identified. It is not that the macroscopic world is immune to quantum laws. Rather, it is saturated by them. Stability is not a given. It must be enforced. By what mechanism? The mechanism is called quantum decoherence. In the early days of physics, we modeled particles in isolation. But in the real world, nothing is isolated. A dust grain floating in the air is under constant bombardment. Billions of air molecules, thermal photons, and cosmic rays strike it every microsecond. Each interaction functions as an effective measurement by entangling the system with its environment. It is an exchange of information. When a particle exists in a superposition of state A plus state B, it relies on a delicate mathematical property called phase coherence, meaning a precise synchronization of its wave function. Think of this phase like a drop of concentrated ink. When the particle interacts with the environment, when a photon bounces off it, that interaction entangles the particle with the photon. The ink of the particle's quantum state leaks out into the vast water of the environment. The information is not lost, but it becomes irretrievably diluted. The delicate interference patterns required for quantum weirdness are washed away by the noise of the environment. The speed of this leakage is terrifyingly fast. For a speck of dust about 10 micrometers in size, floating in a room, the time it takes for phase coherence between superposed states to be effectively destroyed is approximately 10 to the power of minus 13 seconds. This is why you never see a Schrödinger's cat in real life. Before your brain can even process the image, the environment, the air, the light, the heat has already measured the cat trillions of times. Continuous environmental interaction rapidly suppresses quantum interference, enforcing classical behavior. Classical reality, therefore, is not a fundamental property. It is an emergent phenomenon. It is the fossilized residue of quantum mechanics that has leaked its phase information into the surroundings. Decoherence doesn't hide quantum behavior. It dilutes phase information into the environment. But what lies beyond our current models? Our audit has traced the source of randomness to the quantum scale and explained stability via decoherence. But a complete forensic inquiry must acknowledge where the trail goes cold. If we zoom in past the atom, past the nucleus, down to the resolution limit of the universe, we reach the Planck scale at approximately 1.6 times 10 to the power of minus 35 meters. At this scale, our classical notions of continuous spacetime cease to be well defined. The smooth geometry of Einstein's spacetime, the stage upon which all these events play out, begins to break down. Standard physics suggests that at this level, the vacuum is not empty. It is a seething ocean of virtual particles popping in and out of existence, creating what physicist John Wheeler called quantum foam, as described by quantum field theory. Here lies the final unresolved discrepancy in our ledger, the vacuum catastrophe. Quantum field theory estimates the energy density of this vacuum to be enormous at approximately 10 to the power of 113 joules per cubic meter. However, astronomical observations of the universe's expansion show that the actual energy density is near zero at approximately 10 to the power of minus 9 joules per cubic meter. The mismatch is 120 orders of magnitude. It is the largest prediction error in the history of science. It serves as a stark reminder while we have debunked the clockwork universe, our new model is not yet complete. We are staring at the boundary of current theory where the geometry of the container gravity and the behavior of the content quantum mechanics refuse to agree. Below this boundary, our equations stop agreeing with themselves. That's not an answer, it's a limit. This audit leads to a strong conclusion about the limits of prediction in time. If the universe possesses intrinsic randomness, and if macroscopic reality is an emergent phenomenon, then the concept of a pre-written future, the script that Laplace imagined, is physically impossible. This is not just because we lack the technology to calculate it, it is because of a principle known as computational irreducibility. Consider the state space of a quantum system. To fully specify the entangled quantum state of 300 two-level quantum systems, one would require on the order of 2 to the power of 300 complex amplitudes. That number is larger than the total number of atoms in the observable universe, approximately 10 to the power of 80. To simulate the full quantum state of the universe in detail, one would require computational resources exceeding those physically available within the universe. This implies that the universe does not have a shortcut. There is no compressed algorithm that can jump to the end of time and tell us the result. The universe is the most efficient computer for simulating itself. The only way to know the future is to run the process, minute by minute, second by second. The future, therefore, is not a destination that is waiting for us. It is not a reel of film that exists, but hasn't been played yet. It is uncompressed reality. It is being generated in real time. Every interaction and decoherence process contributes to the physical evolution that generates the next moment. If there is no shortcut to the future, then the future is not a file you retrieve. It's a process you run. This brings us to the ontological consequence of our inquiry. For centuries, the clockwork universe of Newton and Laplace offered a strange kind of comfort. If determinism were true, we were prisoners, yes, but we were innocent. Our triumphs and our failures were written in the initial conditions of the Big Bang. We were passengers on a train traveling on fixed rails toward an inevitable station. We had no control, and therefore we bore no ultimate responsibility. The quantum audit strips away that comfort. The rails are gone. The engine is running, the momentum is real, but the track ahead is not laid down. It is being forged in the heat of the present moment. This realization shifts the human condition from one of passive observation to active participation. This is not a romantic freedom to do whatever we want. Gravity and thermodynamics still bind us. It is a structural burden. We are the observers who force the universe to resolve its ambiguities. By interacting with the world, by measuring it, by making choices, we are part of the mechanism that locks probability into history. The universe is not a finished book, it is a live document, and we are the cursor blinking at the end of the line. If the universe doesn't come with a script, what exactly are you responsible for your choices or the reality they lock into place?